If AWS networking has a heart, it is Amazon VPC. You can launch compute, databases, containers, and manage services very quickly in AWS. But if the VPC design underneath them is weak, every other decision becomes harder. Teams start asking why private workloads can still talk out, why public workloads are exposed more widely than expected, why route behavior feels confusing, why security rules overlap, and why production changes feel risky. That is usually not because AWS is random. It is because the team never built a strong mental model for the VPC layer. As a lead engineer, I think about a VPC as a private data center in AWS. Inside that space, you decide the address range, the subnet boundaries, the route behavior, the internet entry and exit pattern, and the security controls around workloads. Once that model clicks, the rest of AWS networking becomes much easier to reason about. Here is the mental model I want you to keep for the entire tutorial. VPC equals your private data center in AWS. Subnet equals a smaller network zone inside that VPC. Route table equals the set of traffic direction rules that decide where packets should go next. Security group equals a firewall around the resource. Network ACL equals a firewall around the subnet boundary. That model is simple, but it is strong enough to carry real production decisions. We are going to use one practical 3-tier architecture all the way through the lesson. A public layer for internet-facing entry, a private application layer for business logic, and a deeper private database layer for state. We will design it across 3 availability zones because that is the standard serious teams use when they want resilience instead of a pretty demo diagram. Let us start with the core structure. A VPC begins with address space. In AWS, that usually means picking a CIDR block for the entire network. In the pattern for this lesson, the VPC CIDR is 10.0.0.0/16. That gives you a large private address range you can carve into smaller, cleaner subnet boundaries. Now we divide that VPC into purpose-built subnets. Public subnets, 10.0.1.0/24, 10.0.2.0/24, and 10.0.3.0/24. Private application subnets, 10.0, 11.0/24, 10.0, 12.0/24, and 10.0, 3.0/24. Private database subnets, 10.0, 21.0/24, 10.0.22.0/24, and 10.0, 23.0/24. Why this pattern? Because good subnetting is intentional separation. Public entry points live in one layer. Application workloads live in another. Databases live in a deeper, more tightly controlled layer. And each layer is spread across multiple availability zones, so one zonal problem does not become a total outage. A subnet is not private just because you named it private. It becomes functionally public or private because of the routes associated with it and the paths that are actually reachable. Now we get to the part that makes the whole VPC actually behave: route tables. Route tables are critical because they are the rules that determine where subnet or gateway traffic is directed. That is not an optional detail. That is the path control system of the VPC. If a public subnet has a default route, like 0.0, 0.0/0 pointing to an internet gateway, workloads in that subnet can participate in internet-facing traffic, assuming the rest of the design also allows it. An internet gateway is the VPC component that enables connectivity between the VPC and the public internet. It does not magically make every workload public by itself. The route path still matters, and so does whether the workload has a public-facing address. Private application subnets usually do something different. They need outbound internet access for package downloads, external APIs, updates, or telemetry, but they should not accept direct inbound traffic from the internet. That is where a NAT gateway comes in. The clean production pattern is to place a NAT gateway in a public subnet in each availability zone, and then point the private application subnet default route at the NAT gateway for that AZ. Database subnets are usually even tighter. In many designs, they have no default internet route at all. Senior teams review route tables as a production control surface. They ask whether the right subnets share the right paths and whether any unintended route has been created. Once routing is clear, we need to talk about traffic control. A security group is the firewall around the resource. In AWS terms, that usually means it protects things like EC2 instances, load balancers, or ENIs attached to managed services. The useful mental model is simple. Which inbound and outbound conversations should this resource be allowed to have? A network ACL or NACL sits at the subnet boundary instead. It is not the same thing as a security group. The security group is close to the workload. The NACL is a broader subnet level control layer. Strong teams use that distinction intentionally rather than treating both as duplicate boxes on a diagram. An elastic IP is a stable public IPv4 address that you can associate with specific public-facing components. In VPC design, you often see elastic IPs used with NAT gateways or other controlled public entry or exit points. Then there is the Elastic Network Interface, or ENI. Think of the ENI as the workload's network attachment inside the VPC. It carries IP addressing, security group association, and the network presence that lets a resource participate in the subnet and route structure. Strong control design means each layer has a clear job instead of every network object trying to do everything at once. Now let us talk about the supporting layer that people often skip because it looks less exciting. DHCP options and runtime identity behavior. A VPC is not only a static diagram. Workloads boot, ask for network settings, resolve names, and behave according to the environment they were given. DHCP options help define things like domain name behavior and DNS resolution defaults inside the VPC. If the workload cannot resolve names correctly, or the VPC DNS behavior is wrong for the environment, application troubleshooting becomes messy very quickly. Engineers sometimes stare at routes and security groups for too long when the real issue is that the workload never got the network context it needed. This is also why ENIs matter operationally. They are not just abstract AWS objects, they are part of the runtime identity of the workload. IP attachment, subnet placement, security group binding, and traffic behavior all come together there. So when we say VPC design, we do not only mean drawing 3 subnet boxes. We mean designing the actual runtime network identity of the workloads that will live in that environment. Now let us assemble the full production pattern. Imagine a regulated digital payments platform serving customers across the United Kingdom. Users enter through a public application layer, but the real application servers stay in private subnets and the databases stay deeper still. The VPC CIDR is 10.0.0/16. 3 public subnets provide the internet-facing layer. 10.0.1.0/24, 10.0.2.0/24, and 10.0.3.0/24. 3 private app subnets provide the business logic layer. 10.0.11.0/24, 10.0.12.0/24, and 10.0.3.0/24. 3 private database subnets provide the state layer. 10.0.21.0/24, 10.0.22.0/24, and 10.0.23.0/24. Public subnets route internet-bound traffic through the internet gateway. The private app subnets route default outbound traffic through zonal NAT gateways in the public layer. The database subnets do not get casual internet paths at all. Public entry services such as load balancers sit in the public tier. The app tier receives traffic only through approved front doors and approved security group paths. The database tier receives traffic only from the application tier on the exact ports and protocols the design allows. That is what good AWS networking looks like. Clear boundaries, clear routes, and clear trust relationships. Good VPC architecture is also explainable under pressure when teams need to investigate failed connectivity or prove a control boundary during an incident. Let me close this the way I would close a real design review. Before you approve a VPC architecture, ask these questions. What is the VPC CIDR, and does it leave room for growth? How are the subnets separated by purpose and availability zone? What route tables are attached, and where does each default path actually lead? Which resources truly need public reachability, and which ones only need controlled outbound access? Are security groups and NACLs being used deliberately instead of redundantly? Which components need elastic IPs, and which ones absolutely should not have them? Do ENIs and DHCP behavior support the runtime identity the workloads actually need? If those answers are clear, the VPC design is probably clear too. And if you remember one production lesson from this video, remember this. Route tables matter because they define the path reality of the VPC. Good AWS networking is not about pretty subnet names. It is about deliberate path control. One last engineering habit is worth keeping. Trace one real request all the way through the VPC and make sure the team can explain every allowed path and every path that should never exist. That habit turns VPC design from memorization into operational judgment before production goes live. It also makes future AWS service choices safer, faster, and easier to defend. That difference matters in every serious production environment.